Let's solve a somewhat challenging problem related to motion in one dimension with constant acceleration. While I'm reading this problem, I'm not thinking about how to solve it. I want to focus on what the problem is about and what exactly is being asked. So let's get started. A rocket is launched straight up with constant acceleration. 4 seconds after liftoff, a bolt falls off the side of the rocket. The bolt hits the ground 6 seconds later. What was the rocket's acceleration? So if you look at the problem, there are no details about the rocket. And all we can see is that the rocket is providing the constant acceleration for the 4 seconds, first 4 seconds, and then the bolt falls off. Also, we don't know what is the size of the rocket or the mass of the rocket. We may not need some of that. We don't know where the bolt is attached to the rocket, what's the height. So we have to make some assumptions here. And like we have seen earlier, we make models. And one of the simplifications we have to do here is that the rocket and the bolt is just a point. So let's say here on the ground, initially this point represents the rocket and the bolt. And really, we just need to think about the bolt because it's the bolt going up and the bolt coming back. All that the rocket is doing is providing the constant acceleration for the first 4 seconds. So the rocket and the bolt go straight up for first 4 seconds. Right, so it still has some velocity here, so it will keep going up, but the gravity will pull it back. The acceleration due to gravity was still pulling it down earlier, but we were given the net constant acceleration, so we didn't have to worry about the gravity. But now it's a free fall. So from here on, the bolt goes up, slowing down, and then coming to a stop. And I'll just draw it a little bit sideways, coming down and falling. So it's still motion in one dimension. I'm just drawing it like this to indicate that the bolt went up and then it came down. So without doing much more, I'm thinking about the problem in two phases. One, while there was a constant acceleration straight up, and then there is a constant acceleration straight down due to the gravity. And there are multiple unknowns here. We don't know the initial velocity going up, which we have to take. We can assume that it's starting from the rest and then there is constant acceleration. So I would say, I'll just say V1 initial. One is phase one. So I'll call phase one and this I'll call as phase two. And so V1 initial is 0. V1 final, we don't know. The delta t is 4 seconds here, so I'll say delta t1 is 4 seconds. The phase 2 V initial, so V2 initial is same as this because that was the velocity when it detached from the rocket. It took 6 seconds for the second phase. So delta T2 is 6 seconds. Let's say A2 is G pointing downward, so I'll just say negative G, which is 9.8 meters per second squared. The acceleration A1, which we do not know, that's what we are supposed to find out. Okay, so at this time, at this moment, I'm thinking that either I can find something from one of the phases which simplifies things, and then if we could do phase 2 first, maybe that simplifies things. I don't really know at this time. Or I might end up getting two equations with two variables, and then I'll have to solve them together. So I don't know this at this time. We have A delta t and the final and the initial. So we can use this equation, V1 final equals V1 initial plus A1 delta T1, right? And that gives us, this is 0 plus A1, we don't know, delta T is 4. So let's say delta x1, how can we use that? We have V delta T A delta x. So we could use V1 final squared equals V1 initial squared plus 2A delta x1. That's the distance or the height it traveled before the bolt separated. And here we get V1 squared equals 0 plus 2A1 delta x1. Ultimately, we just need A1, so we can convert all of these equations as much as possible in terms of A1. So I can write here 4A1 squared equals 2A1 delta x1. And that becomes 16. A1 squared is 2A1 delta x1, or one of these goes away. This becomes 8. So delta x1 is 8A1. We got that, we got this one. Now we can look at the second phase. V2 initial is V1 final, which is 4A1. And the starting position, let's assume this is our origin here. X, in this case, X is vertical. So X2 initial is 8A1. X2 final is 0. It comes back to the ground. So this gives us delta x2 as x2 final minus x2 initial, which is negative 8A1. Delta x2 equals V2 initial delta T2 is half A2 delta T squared. This is the other equation of motion we can use. And we know that A2 is negative G pointing downwards, right? So let's try to plug these in. So this is 18. So if this is 24A1, and we can bring it over here, negative 32A1 equals negative 18G. A1 is 18g over 32, 5.5 meters per second squared. So that is the acceleration of the rocket.